Welcome. So, in the seventh lecture of the series of sequence of real numbers, we study here. So, what is the Cauchy sequence? So, Cauchy sequence. What is the definition of Cauchy sequence? Definition of Cauchy sequence. Okay. Let Sn be a sequence of real numbers. Be a sequence of real numbers. Then Sn sequence Sn is called Cauchy sequence is called sequence if for epsilon positive, if for epsilon positive there exists n belongs to I, there exists n belongs to I such that mod of Sm minus Sn less than epsilon whenever mn greater than or equal to this n. Okay, so if Sn is a sequence of real numbers, then sequence Sn is called a Cauchy sequence if for given epsilon positive there exists n, so integer, so big integer, n belongs to I such that mod of Sm minus Sn less than epsilon whenever mn greater than or equal to n. So we understand this definition by using an example here. So for example, so we take Sn be the sequence is equal to something 1 upon n. So this is the sequence here. Okay, sequence. So what is the sequence? This, put n is equal to 1. So that is 1. N is equal to 2. Then 1 half. N is equal to 3. 1/3. And 1 by 4. 1 upon n. And so just what happens, and so on. So this is the sequence here. So is it Cauchy sequence? Okay, so we learn. So we find already what is the limit of the sequence is limit 1 upon n is equal to, as n tends to infinity, is equal to 0 here. So limit of this sequence is 0 here. Okay, so is it a Cauchy sequence? So this sequence is Cauchy sequence. Why? Because n is so long. N is. So 1 half, 1/3, 1/3. So this is this term is less than this term less than this, and so on up to infinity. So n is so long. So we take mn. After n. Then the difference of two terms is less than epsilon. So very nearest terms. So we take here mn after n. We get Sm minus n less than epsilon. So this is a Cauchy sequence. Okay. So we take another example. So Sn is equal to n square. So this is an example here we take. So that is what happened here. So what is this? Put n is equal to 1. So 1. Then to put n is equal to 4. N is equal to 3, 9. Okay. Then n is equal to 4, 16, and so on. Okay. Is it a Cauchy sequence? So this is not a Cauchy sequence because here n is so long. So long. And this sequence is up to infinity. So n is so long. So if we take m and n, if we take an m and n, and we take some closer elements, so Sm minus Sn not less than epsilon, certainly. Okay. So what is the difference between this? So this is not a less than epsilon. Okay. So we take Mn. Those numbers are bigger. So this condition valued there. So this is not a Cauchy sequence. Cauchy sequence. So these are the very simple examples, and definition is very simple. Okay. So now we take a theorem. We take theorem. Is Cauchy sequence is convergent sequence, or any convergent sequence is a Cauchy sequence? So we take a theorem here. We take theorem. If the sequence Sn is a convergent sequence, then it is a Cauchy sequence. Then Sn is Cauchy sequence. Okay. Okay. Proof. So any convergent sequence is a Cauchy sequence. So that is proving here. Okay. Proof. Okay. Let what is given here? Sn is a convergent sequence. Okay, convergent sequence. Then by definition of a limit of a sequence, so limit of Sn as n tends to infinity is equal to LC. Is equal to LC. Okay. So then what is the definition? Epsilon definition of this limit. Therefore, given epsilon positive, therefore, epsilon positive, there exists n belongs to any integer such that what is the definition of limit? So that is just k minus L is less than epsilon by 2. Doesn't matter, you take epsilon or epsilon by 2. Okay, so epsilon by 2 is small, however small, no doubt. So here k is greater than equal to n here. So k is greater than equal to n. Okay. So thus if mn greater than equal to n, we take m and n are two integers greater than equal to n, we have. So what is Sm minus Sn is equal to, so this can be written as Sm minus L plus L minus Sn. Okay, so L get cancelled, we get this. So by inequality, so this is less than equal to what happened? So this is less than equal to Sm minus L plus what happened? L minus Sn. Okay. So what is the inequality? Mod of A plus B is less than equal to mod A plus mod B. So this can be again right in the form Sm minus L, we take minus sign out and there is a mod, so we get here mod of Sn minus L. Okay. So what is the definition here? Sk minus L less than epsilon by 2. So we get here. So this is less strictly less than epsilon by 2. Again, so this is epsilon by 2. Okay. So therefore, mod of Sm minus Sn is less than epsilon by 2 plus epsilon by 2. So that is less than epsilon. Where Mn greater than equal to n. Okay, greater than equal to n. Then what is this? So this is a Cauchy sequence. So definition is here. Okay, mod of Sm minus Sn less than epsilon where Mn greater than equal to n. So we take here Sn is a convergence sequence. Then we say that sequence is Cauchy sequence. Therefore, sequence Sn is Cauchy sequence. And the proof here, very simple proof of this theorem. Okay, so also we prove another theorem. What is the theorem? Next theorem. So there is a theorem. If Sn is a Cauchy sequence, then it is proved that it is a convergence sequence. This is one more theorem. So also if Sn is a Cauchy sequence, then of real numbers of theorem 2 here, of real numbers then this sequence Sn is bounded. So we know already the every convergence sequence is bounded. Okay, so we know the theorem. Every convergence sequence is bounded. But we prove here the Cauchy sequence is bounded. Cauchy sequence is bounded. So what is the proof? So what is the proof here? So what is given? That Sn be a Cauchy sequence. Sn be a Cauchy sequence of real numbers and for epsilon is equal to 1. So this is our choice. Okay, for given epsilon for our choice we take epsilon is equal to 1, no doubt. So we take epsilon is equal to 1. There exists n integer, n belongs to I, so I is a set of integers such that by definition, since Sn is a Cauchy sequence, then what is the definition here? So mod of Sm minus Sn is less than 1. We take epsilon is equal to 1 here. So here Mn greater than equal to Na. Okay, so we take by definition of Cauchy sequence, we take epsilon is equal to 1. Very simple here. Okay, so this is equation number 1. So okay, hence if m is greater than equal to n, we have so we write here mod of Sm is equal to something mod of Sm. Okay, so this can be written as Sm minus Sn plus Sn. Okay, Sn. So Sn gets cancelled, remaining here Sm only. Okay, no doubt. So by inequality, so this is less than Sm minus Sn plus mod of Sn. Okay, but this is a Cauchy sequence. So this is less than 1. So this is less than 1 plus mod of Sn. Okay, mod of Sn. Okay, where m greater than n. Okay, greater than equal to n. No doubt. So let if m is equal to maximum of mod of S1, S2 and so on. So this is Sn minus 1. Okay. So mod S1, mod S2 and m is the number. So maximum number of this. Okay. So therefore, so certainly mod S1 is less than 1 plus mod Sn plus m. And so this is what happened here. So mod Sn. So Sm, I think Sm, Sm, Sm. This is Sm. So for all m here, so mod of Sm is less than 1 plus mod Sn plus m. So this is upper bound here. So some big m dash something. This is m dash. Okay, m dash something, and this is less than m dash. Therefore, the sequence Sn is convergent sequence. So we take, so this is a Cauchy sequence, and we prove that the sequence Sn is convergent sequence. So this is a very simple proof here. Okay, very simple. So there is another theorem. So what is the theorem? If a sequence Sn of real numbers is a Cauchy sequence, then prove that it is convergent. So this is left for you. Okay, you solve that, you prove that theorem. So this is also very simple theorem. So we take next definition. Summability of a sequence. Next definition, that is C1. Okay, summability of sequence, that is C1. So what is the summability of a sequence? So definition, let Sn be a sequence of real numbers and let sigma n. What is the sigma n? So this is the S1 plus S2 plus S3 up to Sn divided by n, where n belongs to I. Okay, so we say that sequence Sn is a C1 summable to L if the sequence sigma n converges to L. Okay, so very simple definition. Let Sn be a sequence of real numbers and let sigma n is the sum of n terms of the sequence. So S1, S2, S3, Sn plus 1 and so on. This is the sequence. We take first n term and divided by n. So it is called sigma n. Okay, sigma n. So we say that sequence Sn is a C1 summable to L if that sequence sigma n converges to L. That sequence converges to L. So we make one more sequence, that is sigma n. So if you take sigma 1, so that is something S1 upon 1. If you take sigma 2, put n is equal to 2. What is sigma 2? Sigma 2. So that is sigma 2 is S1 plus 1 S2 divided by 2. What is the sigma 3? That is S1 plus S2 plus S3 divided by 3. And so on. So we get another sequence. And this sequence having limit L, then the sequence Sn is a C1 summable. So this is very simple definition. So we take an example of that sequence. Okay, example. If Sn is equal to minus 1 raised to n is equal to 1 to infinity, with the sequence given here, prove that the sequence Sn is C1 summable, or C1 summable to 0. Means limit is 0 here. Okay, so what is the solution? So what is the sequence here? So this is the sequence. So what is the sequence? Sn n is equal to 1 to infinity, so is equal to minus 1 raised to n. So put n is equal to 1, so we get n is equal to 1, minus 1 raised to 1, minus 1. N is equal to 2, plus 1, minus 1, plus 1, minus 1, and so on. So this is the sequence. This is the sequences. So okay, we find sigma n. So what is the sigma n? Sigma n is the addition of n terms and divided by n here. Very simple. So that is S1. So S1 plus S2 plus S3. So that is given. So S1 plus S2 up to Sn. So divided by n. So this is equal to. So what happened here? So this is equal to minus 1 plus 1. Minus 1 plus 1. So this is equal to 1 of minus 1 upon n. When n is odd. So n is odd. 1, 3, 5, 7. So this is odd. N is odd. Yeah. Okay. How it is? So 1. So 1 minus 1 plus 1 minus 1 plus 1 again minus 1 and so on. Okay. So this get cancelled. If n is odd, so there is minus 1 divided by n when n is odd. And if n is even, then minus 1 plus 1 get cancelled. Minus 1 plus 1 get cancelled. If n is even, minus 1 plus 1 get cancelled. So this is 0. So n is equal to 2, 4, 6. So this is even here. So we find limit of that sequence. The sequence. So we make, so sigma n. So we find sigma 1, sigma 2, sigma 3, sigma 4. And we get this sequence. Okay. And what is the limit of the sequence? So we find here n term. So we find limit of n term. So we automatically get the limit of that sequence. So limit of sigma n as n tends to infinity is equal to limit minus limit as n tends to infinity 1 upon n. So this, putting sigma n is equal to this. So this is 0. And limit of this is also 0. No doubt. Limit of this is also n tends to infinity is equal to limit as n tends to infinity 0. So this is 0. So what is this? So limit of sigma n as n tends to infinity is equal to 0. Okay. So therefore the sequence sigma n, so that sequence converges to 0. So this limit, and this is converges to 0. Therefore definition, see definition here. Therefore sequence Sn, this sequence Sn is C1 summable to 0. So this is a very simple example. So we discuss here. So very simple. So we take another example here. take another example. I think something. So this is a sequence. G1 0 1 0 dot dot and so there. Okay, so on. Prove that the sequence Sn is C1 summable to 1/2. So this sequence is given here 1 0 1 0 and so on. Prove that the sequence Sn is C1 summable to 1/2. So what is the sequence given here? So sequence given here is what? Solution. This is 1 0 1 0 and so on. Okay, so this is sequence here. So what is sigma n? Sigma n is what? S1 plus S2 plus S3 plus and so on Sn divided by n here. So what happened here? So what is the sigma n? So this is 1. S1 is 1 plus S2 is 0 plus 1 plus 0. How many times here? N times. Divided by n. Divided by n. So what happened here? So again. Okay. So if n is even. If n is even. So what happened here? 1 plus 1 plus 1 plus n times. N is even. So what happened here? So then 1 plus 1 plus, so how n is even. So if n is 100, so 100. So 1 plus 0, 1 plus 0, 1 plus 0. So how many ones are there? 100 divided by 2 is 50. 100 divided by 2, that is 50. So we say that this is n by 2 if n is even. If n is even, okay, n by 2, and this is a 2. This is n also. This is n also. So this is what? N and n. N is here. And what is this? If n is even, 100 by 2, so n is even, then n by 2. There are 50 ones are there. So 1 plus 1 plus 1 plus 1. If there is 100, so 100 is even. So 1 plus 1 plus 1. How many ones are there? 50. So that is 100 by 2. So n by 2 and n is this. N and it cancels. So this is 1 up. This is 1 up. Okay. This is 1 up. Okay. So if n is odd. If n is odd, then what happened? So this is n plus 1. N plus 1. Okay. N plus 1 divided by 2n. Divided by 2n. Okay. So this is if n is r. So find out limit of that sequence. So limit of sigma n. We make sequence of sigma n and find the limit of that sequence here. So limit of sigma n. So that is what? So this is limit as n tends to infinity. So this is 1 half. Also, what is the limit of n tends to infinity? When this is n is even, so what is the limit of sigma n? Sigma n is equal to limit of. So what happened here? So this is 1 half. N divide here. So 1 plus 1 upon n. 1 half. This is 1 half. So what happened here? Divided by n. So this is 1. 1 upon n. And what is the limit of this? This is 1 half. Okay. So limit of sigma n when n is 1 half. 1 half. Even. Then n is 1 half. Or then is also 1 half. Therefore, the sequence sigma n converges to half. Converges to half. Okay. So we see here what is sigma n? Sigma n That is the limit of 1 half. So that is 1 half. That is 1 half. 1 by 2. So we take here limit of sigma n when n is our n plus 1 divided by 2. If n is divided by n, so that is 1. 1 half as it is. 1 upon n here. So taking limit as n tends to infinity, we get 1 half. To both cases, we get same limit, that is 1 half. Therefore, sequence sigma n converges to 1 half. Therefore, that sequence is C1 summable to 1 half by definition of summability of sequence. Okay, so we stop here. Okay, thank you.